Hi everyone, thank you for this opportunity for presenting this paper titled The Approach of Assessing Time of Preload and Surcharge Removal During the Construction of Embankment over Soft Soils. This paper provides some technical guidance for the assessment undertaken as part of the whole point release process in order to remove the surcharge field of a preload embankment on soft soil. The whole point release process can be broadly divided into 3 steps. Step 1 is to review the monitoring data during preloading in order to assess the degree of consolidation using simple graphical analysis, such as the Ashok and hyperbolic methods. When the assessed degree of consolidation has reached 90% or greater, it is ready to proceed to step 2 to back analyze the soil parameter by curve fitting the settlement time curve. After the back analysis, we can proceed to step 3 to predict the total and differential post-construction settlement. The whole point release can be recommended only if the predicted settlements are less than the design limits for pavement. In step 1, when we are assessing the degree of consolidation during the preloading period, we should be considering settlement data from both extensometer and settlement plate. The extensometer gives the soil layer compression, allow us to assess the degree of consolidation for individual subsoil layer, whereas the settlement plate will only inform us an average value for the entire soil profile. There are 2 methods to assess the degree of consolidation from settlement time curves, namely the Ashok method and hyperbolic method. For the Ashok method, we are plotting the settlement data of time t versus time t minus 1. And the intersection of the data trend line with the 45-degree lines gives the prediction of the total primary settlement. The time step chosen is important. Ideally, we should be adopting at least 20 to 30 days as the time step. Anything less than 10 days may not be giving accurate result. For hyperbolic method, we are plotting the data in this manner: the time divided by settlement versus time. And the inverse of the slope of the data trend line gives the estimate of the total primary settlement. This method is less subjective as there's no need to consider time step, but would normally give a slightly bigger settlement estimate or a lower degree of consolidation than that given by the Ashok method. Data from the Piezometer must not be ignored as part of the assessment of degree of consolidation. For the case with large soil settlement, it is important to correct the pore water pressure reading for any increase in hydrostatic pressure due to the settlement of the Piezometer itself. Otherwise, we would misinterpret the data with greater excess pore water pressure. When we are looking at the back analysis in step 2, it is important firstly to review the soil stratigraphy based on the nearest CPT to the monitoring point, as opposed to using the original soil model for design, because the design model was usually developed for a bigger area with the deepest soil deposits. So using the design model for back analysis may give unconservative results. There are a number of parameters to be considered in back analysis. But the first one I usually look at was to adjust the initial soil over consolidation ratio to fit the overall settlement. While adjusting it, I would also look at how it compares with the undrained shear strength of the soil via Sun-Shep relationship. Or in other words, I'm looking at the corresponding changes to the Sun-Shep parameter S and M in order to give a consistent SU as inferred from the CPT. There are other compressibility parameters such as the compression ratio and the creep strain rate may also need to be adjusted if required, but always compare with the laboratory data to see if the changes are making sense or not. As for the adjustment of the creep strain rate, we need to be careful if it is based on the tail ends of the settlement time curves, as it may overestimate the long-term settlement, because this tail end may not be a pure creep settlement. There may still be a component of primary settlement, even though the soil at this end has reached an assessed degree of consolidation of 90% or greater. As for the assessment of the conductivity, if we are doing a 1D consolidation back analysis, then the coefficient of consolidation, CV, is normally the input parameter. Important to recognize that CV is not an intrinsic parameter, as it varies with OCR. NAVIC 1971 gives some ballpark figure of CV for the different consolidated state and soil liquid limits. If we are doing a final element using chem clay or soft soil model, then the soil conductivity parameters are the initial void ratio, the initial permeability, and the permeability index, CK. The initial permeability can be obtained by different means, or it can be converted from the CV using this equation. The void ratio, the initial void ratio, can be obtained from the laboratory data. The permeability index is typically taken as half of the initial void ratio, but this is not always the case. But it is important to realize that the lower the CK value, the slower is the predicted excess pore water dissipation rate. On this slide, I'm presenting result of using different analytical method to fit the measured time settlement curve. Firstly, I did a simple 1D consolidation analysis, considering creep started at 95% of consolidation. And the result, as indicated by the green curve, fit very well with the measurements. Then I did a more sophisticated analysis, final element analysis, using soft soil creep model with large strain computation that also considered the buoyancy effect. Now, the buoyancy is important because if the field settled below groundwater, the load applied to the foundation soil is reduced because the effective stress is reduced. And the result is also excellent compared to the measurement as indicated by the red curve. So the point I want to get across is that simple method or simple model should be used more consistently with simple analysis, where the complex model is best used with a more comprehensive computational approach. Mixing complex soil model with simple analysis or vice versa may not give desirable outcome. For example, for this purple dashed curve here, I was using a complex soft soil creep model with only small strain analysis computation without considering buoyancy effect. And as you can see, the result is that I overestimate the settlement. The last point I want to highlight on this presentation is that for the 1D consolidation analysis, constant pole construction post surcharge creep strain rate, such as those proposed by LED 1989, is normally used. For the soft soil creep model in Plexus software program, the post surcharge creep is more commensurate with that given by Mercury 1994, in which the creep strain rate vary with log time. This is the end of my presentation. Thank you.